Hey everyone, welcome back to Calc 3. This will be lecture 4 of the course. In this lecture we're going to discuss the cross product of two vectors in space. So previously we discussed the dot product in the last session, and the dot product is a special vector product that produces a scalar as a result of combining two vectors. The cross product is another special product that can be that takes two vectors as inputs, but here the product produces a vector, but a special kind of vector, a vector that's actually orthogonal to the given two vectors that went into the product. So let's just jump into it. So this will be section 1.4, the cross product. Okay, and so we have the dot product from last time. Okay, so we have the dot product from last time. Takes two vectors and produces a scalar. Okay, we talked a great deal about what the dot product's all about in the previous session. This time we're going to talk about the cross product. Right, so this is another product, another operation that you can run on vectors. Takes two vectors and produces a third vector that is orthogonal to the original two. Okay, so that's going to be the main use of the cross product is to identify this orthogonal vector. Right, so if you're given two vectors, you can run the cross product on them, and you'll get a third vector that is orthogonal to the first two. Okay, we'll talk about that in more detail in a moment, but let's take a look at a definition. Let's get kind of formal about this for a moment here. Okay, so we'll let the vector u equal u1, u2, u3, and v equal v1, v2, v3. Okay. Then the cross product of u and v. Okay, so this is the vector sort of written out in component form. The cross product of u and v is given by so it looks we'll discuss how to keep track of this and where this comes from in a moment, but let's just write it out first. So you got u cross v, that's the notation, like the traditional sort of multiplication, and the product looks like this. It's going to be u2 v3 minus u3 v2 times the I vector. Okay. Minus u1 v3 minus u3 v1, okay, times the j vector, and then plus u1 v2 minus u2 v1 times the k vector. Okay, so that's the sort of the formula, if you will, for generating the cross product of two vectors. So not very elegant in itself, but we'll discuss in a second where this kind of comes from and how we will calculate this in practice. So it's important to notice here that we're going from, I wrote this in component form, but the result of the vector is written using the IJK standard unit vectors. Right, but you can just think of this as component 1, and then negative this is component 2, and then component 3. Okay. Now, the cross product is sometimes called the vector product. Okay, remember we had the dot product, which is sometimes called the scalar product. Well, the cross product is called is called the vector product, right? And the reason there is obvious because this is, produces a vector. Okay. All right, so this is kind of the formula for it here, but in practice nobody uses this. The way we want to calculate this is as follows. So how to calculate. Okay, so this is actually based on the idea of a determinant, which is a mathematical calculation that is applied to matrices. Right, so the determinant of a matrix. But because we're not really this is Calc 3, this is a prerequisite, not necessarily a prerequisite, it's a co-requisite probably for linear algebra, maybe a prereq. So it depends on who you ask. But it's a course that there's no assumption that you've had linear algebra and you know anything about determinants when you take this. So we're just going to kind of throw it out there. But basically, U cross V, right? So sometimes the notation looks like this. You sort of have this vertical bar and then your I, J, K, right? Meant to indicate the columns. There's 3 columns here. And then you put the first vector in the middle, so U1, U2, U3, and then the vector you're crossing it against in the bottom, V2, V1, V2, V3, right? And then a bar there. Okay. And so what ends up happening here is you take the determinant here. So this will be a little bit lengthy to write out, but it's quick and easy to perform. It's just a little tedious to write out. So you have U1, U2, U3, V1, V2, V3, and then what we end up doing is we start with the I, right? Because that's the component that we're interested in, right? And then we end up kind of thinking of it as sort of crossing out the column and the row that I happens to be in. And then you do a calculation on this sort of submatrix here. Okay. And then you do the same thing again, except you cross out the J row and column. Okay, so now we're interested in the J column. Sorry, J. So we cross out the J row and the J column, and we run a calculation on U1, V3, V1, U3. And then finally we do the same thing one more time, and then in this case we're interested in the K column. Okay, so we write this back out again. Now in practice you won't have to write this out at all, it's just kind of showing you the structure of how this works. Right, so we cross out the K column and row, and we run a calculation on on the submatrix that's left over. Okay, and so what is that calculation? Well, here what we want to do is we want to multiply on the diagonals, so U2 times V3, and then subtract the other diagonal, minus V2 U3 times I. Okay, so you multiply these two together and then subtract from that the product of these two. Okay, and then you do the same thing again over here. So here it's U1 times V3 minus U3 times V1. Okay, and then the same thing over here. All right, so here we've crossed out the third column, so it's just the first two, U1 times V2 minus U2 V1. Okay, so the product is really just this. It's really just the determinant. Well, so we don't know what a determinant is, but it's really this mathematical calculation called a determinant, and you can kind of think of it as this is just a shorthand for how to calculate this. Now, it's perfectly fine to memorize this if you like, or to reference it, but a lot of times people find it more useful to think of the cross product in this way, because there's a little more meat on the bones here, a little bit more a little more substance versus just cold memorizing something. Okay, all right, let's do an example with some actual numbers. Okay. So let's calculate U cross V v cross u and v cross v when u equals I minus 2j plus k and v equals 3I plus j minus 2k. Okay, so I got two vectors. I want to calculate three different cross products. So I've got u cross v, and then I just change the order, v cross u, and then v crossed with itself. All right, so we're just going to kind of see what happens when we do some of these things. So let's start with u cross v. Right, and so just putting this into the matrix form, I, j, k, and then put the u second, so to be 1, negative 2, 1, right, just pulling that off of here, 1, negative 2, 1. And then the v, which would be 3, 1, negative 2. Okay, and so this is going to be, so the first one we're interested in is the I column, right? So we got to think of removing this column and then doing the calculation on the remaining submatrix. So negative 2 times negative 2 is 4, minus 1 times 1 is 1. Oh, sorry, and it's always minus. Then you do the same thing with the j, right? So it'll be 1 times negative 2 is negative 2, minus 3 times 1 is 3. So 1 times negative 2 is negative 2, minus 3 times 1 is 3. And then finally do the same thing with the k, right? So you hide that one. So it's 1 times 1 minus 3 times negative 2. And so that's 1 minus negative 6. Okay, and we can just simplify this. So that'd be 3i plus 5j minus negative 5j, so plus 5j. And then this will be 1 minus negative 6, so plus 7k. Okay, so there's the cross product. That's u cross v. What about v cross u? Well, it's the same process. The only thing that's changed is the order here. So you have I, j, k, and now this time the 3, 1, negative 2 is in the middle. All right, so you may think that u cross v and v cross u are the same thing, but it turns out they are not. Let's see how they are different. All right, so for the I would hide this, and I would go 1 times 1 minus negative 2 times negative 2. So that's 1 minus 4, right? So you can see that they're flipped. So it's 4 minus 1 here, it's 1 minus 4 here. Obviously going to give you different answers, right? And then minus, and now the j, so it'll be 3 times 1 minus 1 times negative 2. So that'll be 3 minus negative 2. Again, flipped here, right? Okay, so here you had negative 2 minus 3. Here you have 3 minus negative 2. And then plus, hiding the k, you get 3 times negative 2 is negative 6, and then minus 1. Right, so here it's negative 6 minus 1. Right, so again, flipped. It was 1 minus negative 6. Now it's negative 6 minus 1. Okay, and so what do you get? Well, you get negative 3i minus 5j, and then what's the last one? Minus 7k. Okay, so it kind of looks like u cross v and v cross u have this relationship where one is the negative of the other. Right, you kind of see that. This is definitely not a proof, but it's a demonstration that in a specific case, at least it looks like that's what's going on. Now, what about v cross with itself? Well, I, j, k, and then it'll be 3, 1, negative 2, 3, 1, negative 2. Okay. And so, first thing you get is 1 times negative 2, so that's negative 2, and then minus negative 2. That's I. And then it's going to be minus, and then we hide the j, so it'll be 3 times negative 2 minus 3 times negative 2. So negative 6 minus negative 6. j plus, and then it's 3 times 1 minus 3 times 1, so 3 minus 3k. All right, and so what do we get? 0 minus 0 plus 0. Okay, it's the 0 vector. Keep that in mind, this is the 0 vector. All right, so this this would tend to suggest a few algebraic properties of the cross product, right? So first of all, we saw that if you reverse the order, that changes things, and also if you cross a vector with itself, you get 0, at least in this case. So, I mean, it's not hard to generalize that. But let's take a look at a theorem that has a bunch of properties. That's kind of how it works with these things, right? So theorem, so we'll let u, v, w be vectors in space, and let c be a real number. C is in R. Then, okay, so the first thing is what we just saw, u cross v is equal to negative v cross u. Okay, so we saw an example of this just a moment ago. And so this is kind of like, shows you that, so it's not commutative, right? Cross product is not a commutative operation. The dot product is, regular multiplication is, but the cross product is not. Okay, what about this? So u cross and then the sum of two vectors, v plus, this is the vector sum of v plus w. Well, this is equal to the cross product of v plus the cross product with w, right? So it's distributive. This is distributive property. Well, that's nice. Okay, so a vector crossed with a vector sum is the same as the vector crossed separately and then added together. The resultant vectors added together. Cool. Very good. What about a constant? So if I have some scalar c, I want to multiply times the cross product u cross v. Well, it turns out I can multiply c times u first if I want, and then cross that with v, and I get the same thing. It's also fine to do u crossed with c times v. Okay, so it's kind of an associative property with scalars. All right. Item 4 here. So what about the cross product with 0, the 0 vector? Well, it's equal to 0 cross u, right? So in that case it commutes, and it's always equal to the 0 vector. That should make sense. You know, one of the vectors in the product is all 0. Then as you start multiplying everything, it becomes 0, right? So that should be clear. A vector crossed with itself is the 0 vector. And what about the dot product? So if I take u and I dot it with v cross w, right, so this is a vector, obviously, and this is also a vector. When I do that cross product, it's a vector. So what happens when I dot those two? Well, it turns out I get something that is equivalent to u cross v dot w. All right, so that's kind of interesting. So like associativity seems to be somewhat flexible here with the cross and dot product when they're both involved. Okay, so we can cross VW and then dot against U, and we get a certain thing, and we'll get the same thing if we cross U and V and dot with W. All right, well, let's prove a couple of these. Let's prove the first one. So in the first one, we wish to show that, u cross v is equal to negative v cross u. Okay, and so this is just a simple matter of kind of expanding the one and recognizing that when you flip the order, it basically flips the signs. Okay, so let's let u equal u1i plus u2j plus u3k, and we'll let v equal v1i plus v2j plus v3k. Okay. Then u cross v, okay, just kind of pulling this straight off of the definition, is u2 v3 minus u3 v2 I minus u1 v3 minus u3 v1 j plus u1 v2 minus u2 v1 k. Okay, so you got the 3. And, and then just kind of let's do the opposite direction, v cross u. All right, in this case, it's v2 u3 minus v3 u2 I minus, and then it's v1 u3 minus v3 u1 j, and then the last one is v2 u1 minus v1 u2 k, right? So you've got those two. And, just notice that, if I just, this is a v, sorry. If I just look at negative v cross u, well, I have v cross u here, just make everything negative. So negative v2 u3 minus v3 u2 I plus v1 u3 minus v3 u1 j minus v2 u1 minus v1 u2 k. So the supposition is that this has got to be equal to this line. Now, can we see that? Well, yes, easily. All right, we can just do a little bit of a rearrangement. So u2 v3, right? If I multiply the negative through, I get u2 v3 minus v2 u3. Right, and I'm changing the order here, right? So when I multiply the negative through, this becomes positive, and I'm just putting it up front, and this becomes negative, and I'm putting it in the back. Okay. Now here, factor out a negative. All right, when I do that, I get v3 u1 minus v1 u3. Make sure you can see that. I'm factoring a negative out of those two terms to put out front here, and you can see how that changes things. And then multiply the negative through here, and I get v1 u2 minus v2 u1 k, right? And that is clearly the same as this. So that's u cross v. Okay, all right, so pretty straightforward. Now the other properties, we'll just do this one, it's in the interest of time, but these others are also fairly easy to check. Again, these are kind of the kind of proofs that are like very good for elementary proof writers, right? Because they're largely just kind of take the thing you're given, expand it, rearrange it, and put it back together, right? That's what we did here. We took the thing we're given, in this case negative v cross u, we just wrote it all out, rearranged it a bit, multiplied the negatives through, changed the form, and we can see that we can expand or contract it back down to what we want. Right, so proofs don't get nicer than that. Okay. Okay, so just something to note. U cross v does not equal v cross u. Okay, so it's not commutative. Right, so it's a common mistake people make. What it does show us, of course, is that changing the order of the cross product reverses the direction of the resulting vector. Okay, so let's talk a little bit about this orthogonal idea, right? So if I have two vectors, u and v. Okay, you can kind of think of those two vectors as forming a plane, right? There's some plane that these two vectors lie on. What the cross product does is it produces a third vector, u cross v, that is orthogonal to these two vectors, which means that if you think of the plane that these two vectors live on, then this third vector is at a right angle to the original two. Right? So if I do u cross v, it might look like this. If I do v cross u, it's just coming out the other side. Right? It just flips the direction. It flips the direction of the vector, of the orthogonal vector. It's still orthogonal to these two vectors, to this plane, but it's coming out the other side. Okay. And so that's why, u cross v equals negative v cross u, right? Because this is u and v exist on a plane. When I cross u and v, I get one of the orthogonal vectors, and when I cross v and u, I get the other one. Right? I get the one that comes out the same. It's parallel to these two vectors are parallel to one another. They're just heading in different directions. Okay, all right. So that's kind of the idea with cross product. That's how you sort of use it to, that's how you calculate it. Let's talk about another theorem of some of the properties of the cross product, and specifically in relation to some trig functions and some angles, right? So a little more geometric. Okay, so we'll let u and v be non-zero vectors in space. Okay. We'll let theta be the angle between u and v. Okay, so similar to what, kind of the setup with the dot product last time. So if you've got u and v, non-zero vectors in space, and theta the angle between them, then what can we say? Well, this one we've talked about a great deal, but let's formally state u cross v is orthogonal to both u and v. Okay, and that's going to be based a lot on this same picture here that we just talked through, but we'll get into more discussion on this in a moment. Okay. Secondarily, we can say that the norm of u cross v is equal to the norm of u times the norm of v times sine of theta. All right. Thirdly, we can say that u cross v is 0 if and only if u and v are scalar multiples. Right, so if one of the vectors is a scalar multiple of the other, then the cross product is 0. Right, so obviously we've seen the special case of this where u and v are the same vector, but this is a little stronger. It says that actually they don't have to be the same vector, they just have to be scalar multiples of one another. Okay, and then the fourth one is pretty interesting. The norm of u cross v, okay, the norm of that vector is equal to the area of a parallelogram. Having u and v as adjacent sides. Okay, so kind of a big theorem. Let's prove a couple of these. Let's prove 2 and 4. Okay, 1 and 3 is definitely doable. I didn't pick the easy ones. You know, it's just 2 and 4 seem like the ones to look at. So let's start with 2. So we want to prove that the norm of u cross v is equal to this, norm of u times norm of v times sine of theta. Okay, so something that we'll need from last time. All right, what we're going to need from last time is that the cosine of theta is equal to u dot v divided by the norm of u times the norm of v. Okay, so that's something that we talked about last time. We can assume that's true for all uv. Okay, so what we want to start with here is this side. All right, we'll start with this side here. So the norm of u times the norm of v times sine of theta. Well, since this is trigonometry, we can pull in some identities. And what's going to be useful here is the Pythagorean identity. So we know sine squared theta plus cosine squared theta is equal to 1. And so sine theta is equal to 1 minus the cosine of theta, the square root of that. Okay. So that just follows directly. This is, again, this Pythagorean identity. The sine becomes this. Okay, and now let's substitute this in for the cosine here. So we get u, norm of u, times the norm of v, times the square root of 1 minus u dot v over the norm of u times the norm of v. Oops, sorry. That didn't go there. My mistake. So the square root is on the outside of 1 minus. Okay, so... All right. Very good. And we'll have to flip pages here. Okay, so here's where we were at. I just want to make sure we have everything in front of us here. The chain of reasoning is important. You have to see it. 1 minus u dot v over the norm of u, norm of v. Okay, so you have this guy. Okay, that's where we left off. Then leaving the norm of u, norm of v alone on the outside here. Oh, sorry. I was looking at the wrong line here. What we want to do now is we want to actually bring the radical outside and include these. We want to pull these into the radical. So in order for me to do that, this is a product, right? So I've got a product here. So if I want to bring these inside, I can do that. I just have to square them, right? So this is the square root of the norm of u squared times the norm of v squared, right? Minus u dot v over the norm of u times the norm of v. So I can kind of do this. Oh. 1 minus that. Sorry about that. There we go. All right. So all I did was kind of bring it inside the radical, right? And it's multiplied by this whole thing. Okay, and so then this whole thing can be written as the norm of u squared times the norm of v squared minus u dot v squared. Now, how are we doing that? Well, we're distributing this through and then doing some cancellation and then doing some factoring. Okay, so you can kind of see that. So just take this, multiply it by the 1, multiply it by these guys, do the cancellations, and you'll basically get to this. Okay, and now we can start to expand these things into the actual components. Okay, so the norm of u squared is just, this is a three-dimensional vector, a space vector. So it'll be u1 squared plus u2 plus u3, right? So u1 squared plus u2 squared plus u3 squared. That's this guy. And then times the same thing for v. So v1 squared plus v2 squared plus v3 squared. That's this one. Minus, now we've got the dot product here. So remember the dot product is u1v1 plus u2v2 plus u3v3. All right, we'll square that because it's squared. Now this looks terrible, but turns out this works out really nicely. Now when we expand this front piece and then square this piece out here, what we end up with, and it'll take several steps to do it, so I'm just going to kind of cut to the chase here. But you can easily confirm this by just expanding this. What you get is u2v3 minus u3v2 squared plus, and then you get u1v3 minus u3v1 squared plus, and then u1v2 minus u2v1 squared. Okay, and the square root of that. And then, of course, you can see that this is the I component squared. This is the j component squared. And this is the k component squared, right? And so that means you basically just what you've done here is you've got your u cross v. It's a vector, a new vector. It's going to have an I component, a j component, a k component, and all you've done is square them and take the square root. So you've identified the norm. Okay. So again, this is a little bit more of a complex proof, but it's relatively straightforward. The only tricky thing here is, anytime you have to do a callback to something, like this, that can be tricky. And there's also this kind of tricky move of using the Pythagorean identity here, right? So those two pieces are the sort of tricky parts. Other than that, though, it's just plug and chug, right? It's just sort of rearrange things. Let's also look at the item 4. All right, so item 4 says that u cross v is the area of a parallelogram. Okay, it's u cross v. The norm of u cross v gives you the area of a parallelogram, and specifically a parallelogram having u and v as adjacent sides. So this one is actually really easy to prove. You just have to kind of look at it. All right, so I'm going to first draw u, and then some other vector v. Okay, so I've got these two vectors. There's going to be some theta between there, right? Some angle. Okay. Now this height, and so you can see that this would kind of imply a certain parallelogram, wouldn't it? All right, so you can kind of see like the missing pieces here, right? So you could build a parallelogram off of this by taking u and putting the the tail at v, and kind of drawing it out here. So this would imply a parallelogram. And so remember the area of a parallelogram? It's one of those really nice ones. It's basically the same as the area of a rectangle. It's base times height. Right. Well, the base here is straightforward. It's just the norm of u. Right. That's just however long this is, we call that the base. Now the height, however, is this piece here. Right. This height. Right. This is a right angle with u. Now, what is that height? Well, if you can recall back from your trigonometry, this is going to be so this is the cosine here, this length, and this would be the sine, right? But it depends on the length of v. So what we would have here is this guy here is the norm of v. The length of this is the norm of v times the sine of theta, right? And this would be the norm of v times the cosine of theta down here, right? But we're interested in this one because this is the height. Right, so you got base times height is equal to, well, the base is obvious, and then I'm telling you that this is the height. You might have to review your trigonometry a little bit if that's a little fuzzy. Right, but so that basically gets you what you need. Okay, because this guy here, what is that? Well, by property 2, the one we just proved, this is equal to u cross v, the norm. Right, that's what we just proved up above here. Okay, so we just showed that u cross v is the same as this. Right? We can easily see that this here is the base times height for a parallelogram constructed in this way, and so you've got the area. Take the norm of the cross product and you get the area of the parallelogram that the two vectors imply. All right, very good. Excellent. Let's do an example or two. Okay, so let's start. Let's find a unit vector. Find a unit vector that is orthogonal to both u equals I minus 4j plus k and v equals 2I plus 3j. Okay, so we want to find a unit vector that's orthogonal, right? So this is kind of a two-step. But first, we can find the orthogonal vector just by using the cross product, right? So you can do u cross v or v cross u. Right, and so we'll just do u cross v. That'll be 1, negative 4, 1, and 2, 3, 0. Okay, so you get 0 minus 3i minus 0 minus 2j plus 3 minus negative 8k, right? So again, just kind of going through here and crossing that out and then crossing that out for the middle component and then crossing that out for the third final component. Right, and so what do you get? You get negative 3i plus 2j plus 11k. Okay, so this vector here is u cross v, and it's orthogonal to u and v, to both of those vectors. It's orthogonal to both of those vectors. But it's not necessarily a unit vector. So how do we find the unit vector? Well, remember, a unit vector can be found Cheapers. A unit vector can be found using, basically take the vector and divide it by its norm. Okay, so that's what we're going to do. So first we need the norm of u cross v. All right, that's going to be negative 3 squared plus 2 squared plus 11 squared, square root of that. And we get 9 plus 4 plus 121, and we get 134, square root of 134. Okay, so not a nice, pretty easy number, but that is the length of u cross v. And so then an orthogonal unit vector would just be u cross v divided by its norm. Okay, so it's just 1 over the square root of 134 times the vector negative 3 to 11. Okay, and so you can write in component form. You can write in IJK form if you like. So I'm just going to write it like this. Negative 3 over the square root of 134, comma, 2 over the square root of 134, comma, 11 over the square root of 134. That one works. Okay, so that's a unit vector that is orthogonal to two given vectors, u and v. All right. Let's see. Let's see what to do next. Here's another example, kind of a trickier example. I'll just kind of give you the sketch for this one. So let's show that the quadrilateral, okay, with vertices at the following points is a parallelogram. And find its area. Okay, so the points are, the A point is 520. The B point is 261. C is 247. And D is 506. Okay, so you got these 4 points. And so you can pretty quickly confirm, and I'll just leave this to you, easy to confirm, this is just a slope argument basically, that AB, the line formed between these 2 points, is parallel to CD. Okay, so these two together form a line, and it's parallel to these two, the line formed by these two as well. And, right, so you get that one, and AD, right, if you take A to D, that's all parallel to CB. Okay, so basically what we know now is that we've got this kind of thing where you've got this line is parallel, that line is parallel, and we know that these two lines are parallel as well. What we don't know is the lengths. Like we need to, we would want to confirm that the lengths are the same, right? I.e., that they're a parallelogram and that they all intersect. And they kind of, this kind of thing you can do pretty quickly. You can just sort of plug some of this stuff in and play with it. And so, let's see here. Let's flip pages here. So the question is more about the area, right? So let's assume we can get to the point where we know this is a parallelogram, right? And you've got, 4 sides here, and one of them is AB, and the other one is AD, right? So you've got AB and AD, and so this one would be CD over here, which you can get to pretty quickly, and this one would be CB. All right, so that kind of means that this is B, this is A, this is C, and that's D. All right, so you can kind of get to this picture pretty quickly by just sort of doing a little bit of reasoning. Okay, now what's the area of this? What's the area of this? Well, remember the area is the norm of U cross V, where U and V are adjacent vectors. Meaning they share a vertex, right? That's what adjacent means. All right, so let's just run the cross product on AD and AB. All right, so let's look at AB cross AD. Okay, so we'll have to figure out what the vector AB is. Okay, we'll have to figure out what the vector AB is. So AB is equal to, basically you're going to take B and you're going to subtract off A. Right, so you would take 2 minus 5, and I'm kind of looking at this off to the side, but this would be 2 minus 5I plus 6 minus 2J plus 1 minus 0K. Okay, and you'd get negative 3I plus 4J plus K. And you could do the same thing for AD. Right, so for AD, it would be basically 5 minus 5, I plus, and then 0 minus 2, J, and then plus 6 minus 0, K. Right, so again, just kind of subtracting the points here. Okay, and then what you would end up with for AD ultimately is 0I minus 2J plus 6K, right? So these are the two vectors of interest, right? That's this guy here and this guy here. Right, so let's cross those and then take the norm, and we will get to the area of this. Okay, so AB cross AD, all right, so I, J, K, and then your AB is the first vector in, so negative 3, 4, 1, and then it's AD, which is 0, negative 2, 6. Okay, and so these are slightly, like a little bit larger numbers than what we've had before, so it's 24 minus negative 2i plus negative 18 minus 0j plus, sorry, that's a minus. Okay, and then plus 6 minus 0k, right? And so what do you get here altogether? You get 26i plus 18j plus 6k. Okay, so that's AB cross AD. Now what we need is the norm of that. So the norm of AB cross AD, it's just going to square all these things, add them up, and take the square root, right? So 26 squared plus 18 squared plus 6 squared. All right, that's something that's a little bit of a mess. But we can get down to this. It's 1036 square root of that, and that's approximately 32.2. Okay, so the area of the parallelogram is 32.2. Okay. All right. Excellent. Right. So these are just sort of some of the elementary properties of cross product. Right. And you will be using the cross product throughout Calc 3. We're just kind of winding up here. One more topic before we go, and that's something called the triple scalar product. Okay, so definition. Let U, V, and W be vectors in space. Okay. Then, so basically U dot V cross W. U dot V cross W is called the triple scalar product. Okay, this is called the triple scalar product. Okay, and there's a couple ways to find this. I mean, you can do it just by finding V cross W and then dotting it against U. That's fine. There's also some kind of sort of clever ways to do it. Right? There's a clever way to do it. So if U, the vector, is equal to U1, U2, U3, V is equal to V1, V2, V3, and W is naturally W1, W2, W3. Then we can calculate the triple scalar product using this nice little technique. Then the triple scalar product is, so you've got your U dot V cross W. So kind of similar to the way you do the cross product, except instead of IJK, you put in U1, U2, U3. And then it's V1, V2, V3, W1, W2, W3. Okay, and so this is probably intuitive, but what happens here, right? So instead of, normally you have IJK up here, so you're sort of multiplying each of them by I. So in this case, you'd be multiplying the first component by U1, and then you multiply the second component by U2, and you multiply the third component by U3, right? And you add them all up, you get basically the triple scalar product. Right, so it would be, let's see here, it'd be V2 W3 minus W2 V3, right? So that's when I hide here. And then I multiply that times U1. And when I say multiply, I mean dot product, right? Well, this is a component, so it is just multiplication, right? That's the dot, though, piece of it. And then it's minus, And now I'm hiding those two, so V1W3 minus W1V3 times U2. And then plus V1W2 minus W1V2 times U3. Right? And then if I multiply the U1s through here, right, you can see what happens, right? This distributes, that distributes, that distributes, right? And then in the end, you just add it all up and you get the dot product. Or sorry, you get a scalar, right? You get the triple dot, the triple scalar product, which is a scalar. Okay, very good, very good. So we'll come back to the triple scalar product as well. Again, we're just kind of winding up, introducing some topics. One of the interesting things about the triple scalar product is that just like the norm of the cross product was the area of a parallelogram, the triple scalar product is the volume of a parallelepiped. So let's talk this through. So theorem, the volume of a parallelepiped with U1, U, V, and W adjacent vectors, edges, we'll say edges. They're vectors, but edges is better, is given by, well, the volume is equal to the absolute value, right, because the triple scalar product is a scalar, so it's the absolute value of U dot V cross W. And so this is the triple scalar product, just the absolute value of that is the volume of a parallelepiped. So let's talk through this thing. Let's draw a picture. This is a super easy proof, again, but only because you can kind of see it when you draw it. So here I've got my V vector. Here I've got my W vector. Okay, and then let's say I've got a third vector U. It kind of comes up like this. Okay, now it's important to draw this picture reasonably well, so I'm going to try really hard here. So here's there's a sort of a plane that's implied with W and V. Again, this is just the parallelogram that we talked about last time. So you get a parallelogram with V and W. Okay, now you can think of, edges coming up off of this, right, like so. And there is a parallelepiped that's implied here. Okay, so basically you can think of, for people who don't know what a parallelepiped is, it's kind of like you've got parallel opposite sides and top and bottom and side to side and front to back. It's kind of like a parallelogram but in 3D. I call it parallelepiped. Okay, now what's the volume of a parallelepiped? Well, the volume of this is the base area times the height, right? So the base area, you can think of this as the VW plane down here. So that area is the area of a parallelogram. Okay, so we know that the base area that's going to be U cross V, or sorry, V cross W, right? These two vectors, if you take the cross product of those and the norm, then you get the area, right? So it's the base area. Now we need to know the height. Now the height is not the length of U, remember. The height here is, there's a surface implied up on top that's parallel to the surface on the bottom. And so the height is the height from that surface down to this plane. All right, so that's the height. Okay, but what is that in terms of the vectors U, V, and W? Well, we talked about this last time. This is just the projection This is not easy to see, so I mean, if you're not seeing this, that's okay. This height is just the projection of u, right, this vector, onto v cross w, right, which is this piece down here. And of course the norm of that, right, that's a vector, right? So the height is just the projection of u onto v cross w, right? The norm of that, that's a length, the length of that projection. Right? Does that make sense? Right? Because this vector here is orthogonal to v and w, right? So that's the v cross w piece, and then the projection of u onto that is just going to kind of scale this length down, right? Okay. You can also think of it like this. You can think of it by putting it outside here if you want. This is the projection out here. Right? You're just taking that and projecting it down onto this v cross w vector. All right, so that means you've basically got this, the norm of v cross w times the norm of the projection of u onto v cross w. That must be the volume. But what is this projection of v cross w business? Well, what do we get here? We got the v cross w out front. Now, if you look back, you'll see that the projection of u onto v cross w, there's a nice way to calculate that, and it is u dot v cross w divided by the norm of v cross w. Sorry, that's an absolute value because that's a scalar. Apologies, that's an absolute value. All right, now, and obviously you get some cancellation, and so you get u dot v cross w, absolute value, equals the volume. Okay. All right, so that is the parallel pipette volume based on UVW adjacent vertices and the cross product and the projection of u onto the cross product. Probably the trickiest part of this is thinking about this projection piece. Okay, but just remember, v cross w is a vector that's orthogonal to both v and w, which means it comes out of the plane here, and then you're just projecting u onto it. That's the projection. That's the height of the parallel pipette, and then that's how you calculate the volume. You just take the base area times that height. All right, so that is where we'll end it. Next time we'll talk about, we'll kind of move into lines and planes in space and do a little bit, try to get comfortable with some more of that spatial geometry and just getting comfortable with how to talk about lines and planes and their intersections and where they come together and meet and da-da-da. So until then, take it easy, and we'll talk to you next time.